Hello everyone, welcome to this live series on revenue management and pricing. This is Parshan Pakiman. I am a PhD candidate in information and decision sciences at the University of Illinois at Chicago. Today I want to talk about self-adapting robustness in demand learning, which is a joint work with Professors Beryl Chen and Stefanos Jason, and my PhD advisor, Professor Selvan Nadarj. Let me motivate our business problem. Consider a dynamic pricing and demand learning scenario where a decision maker wants to compute a policy pie to maximize its revenue over a finite planning horizon with the length of t. Setting the price in the initial stage where there is no past data, customers arrive and they exhibit different demand realizations. Each demand realization depends on the price that is set at the initial stage and depends on theta naught, where theta naught here is the true demand parameter. After collecting this demand observation and collecting the revenue observed in this time interval, we go to the second stage and we set the second pricing decision, which is denoted by P2 of pi. In our setting, theta naught is not typically known to the firm, and the data generated in this process can be used to identify theta naught from the historical data. Throughout, we assume the demand model parameter is unknown, but it belongs to a finite set denoted by theta. Let me formalize this problem. When theta naught is known in an idealized setting, we maximize the expected total revenue from the policy pie, where the expectation is taken with respect to demand trajectories and price decisions, where price decisions could depend on the past price decisions as well as demand observations. We refer to this optimization, its optimal solution, as complete information policy, and it is idealized and may not be used in practice. Let me connect the current configuration with the existing literature. In the literature, typically, the number of stages is large, though in our setting, we consider a relatively small number of stages. Also, the price adjustment in the existing literature happens at the customer level. However, in our setting, the price can be set at the pre-specified point in time. For example, if we plan over months, maybe we can only set the prices at the week level. Therefore, every customer who arrives at the given week observes the price that is set at the beginning of that week. This is a key difference between the existing literature and our setting. This problem arises in practice, for example, in brick and mortar stores. So motivated by this, we consider this new framework and analyze how policies can perform in this setting. In the existing literature, revenue loss is constant and is independent of the customer arrival, which is denoted by M1 to NT. However, in our setting, when the prices are set at the pre-specified pricing points, revenue loss depends on the customer arrival and can be linear in the worst case scenario on M, where M here is the total number of data points. Now I want to describe two pricing policies that are relevant in our setting. The first one is based on distributionally robust optimization, where we maximize the expected revenue with respect to the worst demand parameter. This policy is practical unlike the complete information policy. It is risk averse. However, it is static and it doesn't adapt to data, and it can be conservative. On the other hand, we can look at the follow the leader approach, which constructs an estimator of the true demand model from the data that is revealed, and it maximizes the expected revenue with respect to the estimator theta hat t. This policy is practical, it adapts to data, but it can be risky when the volume of data is low, and it requires prior knowledge about theta hat t when t equals 1. At the initial stage, there is no data, and this prior knowledge is needed for the follow the leader approach. Looking at the spectrum, that the red region shows high demand ambiguity and green region shows low demand ambiguity, we observe that risk averse property of SR is useful in the red region, while in the red region, follow the leader can be risky because demand ambiguity is high. However, in the right side, the green region, a static robust can be conservative because we have a lot of data points and demand ambiguity is low. In this case, follow the leader is favorable because it adapts to data and it can achieve near optimal performances. What we want to do, we want to provide a self-adaptive policy that transitions from SR to follow the leader based on the arrival data. And it leverages both a risk-averse property and regret minimization properties in follow the leader and SR. Let me motivate our problem and motivate our adaptively robust learning, which breaches the gap between SR and FDM. On the x-axis, I have periods, and the y-axis, we have the demand model ambiguity. As time progresses, demand ambiguity decreases, and at some point, we observe enough data points where we can identify the true demand parameter theta naught. The ARL policy self-adapts to data in a sense that it hedges the risk exposure of the seller when we are in the red region with high demand ambiguity, and it gracefully transitions to regret minimization when we have low demand ambiguity. Now, I want to describe what is the underlying idea in the ARL policy. This policy depends on the self-adapting ambiguity sets. These ambiguity sets are constructed in a stochastic manner that update based on the online arrival of data. In the red region, at the initial stages where we have limited number of data points, this ambiguity set equals to the entire demand models. And as time progresses, we eliminate or add different models to this set based on the observed data. This set converges to the singleton theta naught with a high probability when the number of data points are sufficiently large. Let's get into the details of how we construct the self-adapting ambiguity sets. We construct the set by considering all parameters, all demand parameters theta, where Kc of theta is less than some data-driven threshold. And we also add the minimizer of Kc in this set. The Kc is a distance between empirical and model-based means. And this data-driven threshold is computed in this way, and its rate depends on 1 by the S-square total number of data points that are revealed up to time t-1. This data-driven threshold is used to eliminate the demand models in the uncertainty set, and it depends on some constant like 2, m, t, and psi of c, where psi of c is an increasing function of c, where c is a deterministic distance between theta naught and the closest model to theta naught. Having this uncertainty set, we can explore how its cardinality changes over time. Here I draw the cardinality of the uncertainty set U hat t for different times. Initially, this set has all demand models, and as data arrive, it eliminates demand model, and at some point, it equals the singleton theta naught with a high probability. The time in which we observed enough data to identify the true demand parameter, we refer to it as a demand identification time. Specifically, T tilde equals the first time in which the amount of data revealed is greater than or equal to this constant. If this condition never happens, then we set T tilde to T plus 1. Therefore, the demand identification time is the first time that ARL policy identifies the true demand parameter. Now, using the ambiguity set that we discussed and the ARL policy, we explore how the performance of SR, FDL, and ARL policies compare. Let's go back to our spectrum we discussed with the red region of high demand ambiguity and green region of low demand ambiguity. When the volume of data is low for all demand parameters, means that we cannot eliminate demand parameters from the ambiguity set. Therefore, SR objective equals AR objective. This is the comparison between SR and ARL in the red region. Now, similarly, we can construct results for the green region. When the volume of data is sufficiently large to eliminate all demand model except the true demand model, with high probability we can show the ARL objective and FTL objective coincide. For every policy and T, regardless of the red region or green region, we can show that ARL's objective is closer to the complete information objective than the SR objective. Also, we can show that in a worst case sense, the ARL's objective is closer to the complete information objective than the follow the leader objective. Now, let's discuss the regret performance for the ARL policy. The regret bounds for ARL, it depends on the arrival pattern of the customers. This is not typically the case in the literature for regret analysis. In our setting, regret, the total expected revenue between complete information policy and ARL policy is upper bounded by the big O of the number of customers arrived before the demand identification time T tilde. Also, for the regret, we can show that the absolute value difference between the follow the leader total expected revenue and ARL policy is upper bounded by the same rate. To give the example, we consider this good case scenario where the volume of data prior to demand identification time is a big O of ln of the total number of observations. If this condition happens, then the same rate applies to the regret. Therefore, a regret analysis depends on the arrival pattern of customers. So with this, ARL policy exhibits favorable properties in terms of regret and risk. Now, let me summarize the policies that we discussed and then compare the numerical performance of these policies. We discussed the complete information policy, where this policy is optimal, but it is impractical. We discussed SR, practical, it is robust, it is static, and it is conservative. We discussed the FTL policy, where FTL is practical, it can be risky, but it adapts to data, and it requires prior knowledge. The ARL policy, which we described in the last few slides, it is practical, it is robust, it self-adapts to data, and it doesn't need the prior knowledge. Now, let me describe the computational setup we considered and then compare these policies. We compare the performance of the policies on 1080 instances. We use SR, FTL, and ARL policies, as well as UCB as a benchmark. We analyze the effect of following factors on the policy performance. Price informativeness, which I described soon in the next few slides, and then arrival pattern of customer. We consider how total traffic affect the performance of policies. We vary the demand model. We consider linear and exponential demand models, and we change the demand noise. I should notice that in the paper, we consider a modified version of ARL for the numerical analysis, but for this presentation, I refer to both modified and the vanilla version as ARL. Now, let me describe two performance metrics that we use to compare the performance of these policies. The first one is expected gap. The expected gap is the difference between the total expected revenue obtained from a policy pi, which is expressed as a percentage of the total complete information expected revenue. The relative value at risk is a measure of risk, which is a 95% value at risk of the total revenue obtained from policy pi, and this also expressed as a percentage of expected total complete information revenue. Let's look at the results. First, I consider the informative prices. By informative prices, I mean the revenue and demand models are well separated. And if we play a price that allows us to see demand observations to identify the true demand parameter from the rest of models. Here, all the models are well separated, and we refer to them as informative prices. In this scenario, I plotted the distribution over instances, where in the left-hand side, we have the expected gap, and in the right-hand side, we have relative value at risk. We observe, in terms of expected gap, which is total revenue metric, ARL and FTL exhibit similar performance, and both are near optimal. But in terms of their value at risk, the ARL significantly improves upon follow the leader. Specifically, it improves the third quartile of the R-var from FTL. The SR in this setting achieves a larger expected gap as well as R-var. Now we look at the partially informative prices. Here, I refer to partially informative instances where if we play the price 0%, that price may allow us to eliminate the red and green model, though pricing policies could be confused between the blue and orange model. In this setting, we look at the same distribution we observed before. We have the expected gap in the left and the R-var at the right. The ARL and follow the leader exhibit similar expected gap, say they obtain similar total revenue, but in terms of risk, ARL significantly improves upon follow the leader. SR in both settings, informative and partially informative cases, achieve larger expected gap and R-var. Here, R-var improves the third quartile and median of value at risk compared to the follow the leader when we observe the partially informative prices. Next, we compare the performance of these policies for different arrival patterns. We observed overall that ARL is more stable compared to FTL for different arrival patterns. Here we have the exponentially decreasing arrival pattern, which we see the expected gap of two methods are comparable. When we go to the R-var and risk, we see that ARL significantly improves the median and the third quartile of R-var compared to follow the leader. This shows that not only ARL achieves high quality total revenue, it also significantly reduces the risk. Finally, we compare ARL with UCB. Overall, we observe that ARL beats UCB. In a setting that we have exponentially increasing pattern, UCB and follow the leader achieve comparable performances. And in this setting, we observe that ARL significantly improves in terms of expected gap and R-var upon UCB. For partially informative prices, UCB and ARL exhibit comparable median R-var, though ARL achieves a substantially better median expected gap compared to UCB. Let me summarize the talk with few bullet points. Motivated by practice, we considered a new dynamic pricing setting where the price decisions are adjusted at a pre-specified time over a finite selling horizon, which is different from the literature. In this setting, the use of suboptimal prices based on wrong demand models when demand ambiguity is high could result in a significant loss in revenue. For example, when demand ambiguity is high, we may have a wrong demand model that leads to a suboptimal price, where the suboptimal price could apply to a lot of customers and that affect a significant revenue loss in terms of total revenue. We develop an ARL policy based on self-adapting uncertainty sets that stochastically evolves upon the online arrival of data. In the red region with high ambiguity, it's similar to a robust policy, and in the green region with low demand ambiguity, ARL policy is similar to the FTL policy. Finally, in terms of theoretical properties and numerical performance, ARL manages the risk and the regret, while SR and FTL only manage either of these metrics. Thank you very much for your attention.